Hi, and welcome to the first Data Structures and Algorithms lab. This lab we're going to talk about first the historical part and then about linked lists. Okay, so first of all, let's see what these lab rules are. Okay, so this lab has two parts. The first part is the data structures and the second part is algorithms. After each part, we'll take a small test. I'll give you more details 1 week before the test. And for each lab, I would like you to upload what you've done during the lab on Moodle. So then that will take up 1 point of the lab grade. So if you submit all of the labs, then you will have 1 point. If you submit half of the labs, you'll have 0.5 and so on. This is not a bonus, but part of the grade itself. And for each lab, you need to upload it until the end of the week. And the final grade is made up of two parts. It's 35% the lab grade and 65% the final exam. All right. The rules of this lab are as follows. If you cannot attend the on-site lab, just email me if you haven't emailed me already, and that is needed for me to check your presence in the presence sheet on Google. And after you email me, you have two options. You can either go with another teacher and recover the lab, or watch a YouTube video with the lesson, just like this one. And at the end, upload on Moodle what you've done during the lab. And the most important rule is to ask questions. Anytime you have a question, just either post it here as a comment on YouTube or email me or give a sign, because that's my purpose here, to help you get better at this stuff. And I'd really like to help you as much as I can. Now, why are the data structures and algorithms, important? So, they're useful for, there are two things. In practice, as a web developer, I use them at least once a month. So they are quite useful. But the way we're going to do them in this lab is different from the way they are used in practice. And in this lab, we're going to learn how they work behind the scenes, but in practice, you just use them. You already have them written. Let's see an example. So in this lab, we're going to talk about lists. And here on the left side is what we're going to do at the lab. We're going to write functions for the list. And here in the main function, we will use the functions. In practice, on the other hand, you don't need to write the functions yourself, because you already have them written somewhere. In C++, you have the list header, which contains this list object. This list object has two methods, it push front or push back, which are like insert first and insert last that we're going to talk about later in this lab. So basically, in practice, you will use them, but you don't need to know how they work behind the scenes. But knowing how they work behind the scenes can help you understand which data structure to use and when to use them. All right. And the second thing they are useful for is job interviews. It's quite common at job interviews to either get a problem, a technical problem that requires you to use data structures or algorithms, or they might just ask you. The interviewers might ask you, what data structures do you know? So, yeah, I hope they are useful for you. And also, there is a third line which I didn't include here. In this lab, what I hope is that you improve just, if only a little bit, your programming skills. I'm very happy with it. So, yeah, but that's the classical argument to learn stuff. You'll get to program better later on. All right. So we talked about the lab rules and why are data structures and algorithms useful. Now, before we move on to the linked list, we need to talk a little bit about addresses and pointers, because we'll use them a lot. And I know it's a tough topic, but I'll hope this will make it a little bit clearer what they are. Okay, so first we're going to talk about addresses. And when talking about addresses, we need to know what the RAM memory is. It's like a small piece of circuits that is in all of the computers, including phones, have RAM memory. And its purpose is to remember all the variables of all the programs. So it's where the variables live. So if my computer is running Chrome, my program, and Windows, all of the variables of Chrome, my program, and Windows will be inside this circuit, this RAM memory. So the RAM remembers all the variables. And you can imagine this RAM memory like a huge array of variables. So in this example, we have two variables, A and B, and somewhere in this huge RAM memory, we will have A and B and their values. All right. And what's important is that each variable has a number. So you have the first variable 0, then variable 1, then variable 2. And in this case, our program has variables from 300 to 400. And A is variable 300 and B is variable 301. Actually, this is not technically correct. B would be actually 304 or 296, but let's keep it this way because it's simpler to think this way. So each variable has a number, and the address of a variable is actually the number of the variable. So the address of A is 300. And the address of B is 301. Now, you can obtain the address of a variable using the ampersand. Here, the and sign means address of. So this is read like address of A. If we would try to print the address of A, if the memory would look like this, it would show 300, the address of A. If you try to run this program on your computer, it will definitely show a different number. And the number would probably be huge because you have a lot of variables in the computer. But this is the main idea, that the address of a variable is its number in the whole memory. Now, what are pointers? Pointers are a special kind of address of variables. So int star p means p is a pointer, and pointers don't contain numbers, but they contain addresses. So if we say int star p, we say that p will contain the address of an int variable. And if we do p, we assigned to p the address of a, here our variable p will store the address of a, which is 300. This 300 is the address of a. And you can use star p. So with p simple, we refer to this variable, the variable p, but with star p, we refer to the variable pointed by the address p. So in this case, star p is variable 300, which is a. So in this case, if we do star p equals 15, it will change a to 15. It will change the variable at address 300 to 15. All right. And also you can use star p not only to change the value of the variable, but you can also read the value of the variable. So printf %d star p will print the value at address 300. What do you think this will print? Well, star p is 15, so it would print 15. All right. So here, when should we use pointers? So it's not like only cool people use pointers. I don't think that way. I really saw pretty ugly code with a lot of pointers. It can be simplified, and I don't like complicated stuff. But sometimes you need pointers. And you need pointers in two scenarios. If you have functions that have parameters which change inside the function, we'll see an example soon, you need to use pointers. So when function parameters change, we use pointers. That's only in C. In C++, you can use references, and in other languages, there are some other stuff, but mainly we use pointers for this lab. And you also use pointers when you have linking between objects. We'll see later how in linked lists, we need pointers to connect them with each other. All right. And even if in other languages like Java or JavaScript or Python, we don't have pointers, they actually are a lot of pointers behind the scenes, but they are called references. So you kind of use them sooner or later. So let's see an example of a function that changes the parameters. But first, let's see a task. Let's say we have variable a equals 10 and a variable b equals 5. And we want to swap A with B so that A becomes 5 and B becomes 10. We change those two. We want to swap them. And in regular code, we would take an auxiliary variable and first put the value of A in the auxiliary variable, then change B to 10, change A to 5, and then put the auxiliary variable in B. So basically we do a swap. And this works just fine. But if you try to do it as a function, to use it in many places, let's say we have a function swap that takes two numbers and we want to swap them, and here use the function instead of putting the code. Do you think this will work? Like here we do the exactly same thing, but using a function. And the answer is not really. And this is because if we have two variables and call a function, the function parameters are just copies of the initial variables. So if you have A and B in the main program, you would have another A and B in the swap function, which are copies of this one. So if we do here the swap, we would swap the A and B from the swap function, but the original A and B would still remain the same. It will still print 10 and 5. We didn't manage to swap them. But if you want to swap them, then you can use pointers. And this means that A and B will be the addresses of the original A and B variables. So if here we have A equals 10 and B equals 5, we have, oh, I put them reverse here, sorry. And then you call swap address of A and address of B. Then in here, we would take their addresses. And instead of using A and B, we put star A and star B. So that way, it's like we're using the original A and B variables. If you have any questions, don't forget, just pause and send them to me. I'll answer as soon as I can. And thank you. I know this isn't the perfect lab, and maybe we can improve it together. Alright, moving on. The next step we are going to talk today is about singly linked lists. The way I like to view linked lists are like treasure hunts. In treasure hunts you have hints, and every hint tells you where the next hint is. So let's say if the first hint is you find it in a cold place, then you look in the fridge and you find the second hint, which says where the monsters hide. So you go to the closet and there you find the big treasure, the CD with Manele. In a similar way, moving from one hint to the next, in linked lists we have elements, and each element will tell us where the following element is. So here we will have the list 10, 7, 12. And linked lists are just a way to store multiple elements, and each element is called a node. Here each box is one node, and each node has a key. Here we used integers, these 10, 7, and 12, and the pointer to the next element. So each item knows where the next item is. Okay, if we dive a little bit deeper, if we look at how this list looks in the RAM, here we defined a structure called the node for each node, and each node has a key, an int, and a pointer to the next node. So this one is a pointer to the next node. This is how you write in C++ without typedef. If you're using plain C, which I don't recommend, you also need to put a typedef before and here add the node as well. But this should work. So if we have this list, in the memory it would look like this. So we have the 10, and the next is an address of the next element, 700. And 700 we have key 7, and the next is at address 300. If we go there, we have a key 12, and the next is null. So there's nothing more left. As you can see, the order of the list is not necessarily the same as the order in RAM. So in RAM you can have any order, it doesn't matter, because each element knows where the next one is. And this way, whenever we need a new node, we just create a new node and add it to the list. So this is a difference between regular arrays and lists, and that is, if you don't know initially how many elements you have, with lists you just add more as you go. You don't need to specify it at the beginning. Okay, so each element contains the address of the next element. All right, and furthermore, we need also a data structure, a struct, for storing the head and the tail of the list. Actually, we only need the head because when you know where the list starts, you can find all the other elements. But the tail is also included in the structure, so we also keep track of the tail. Like here, head is 150 and tail is 300, the first and the last element. And we need to know the last one because some operations will be faster if we already know the tail. For example, adding a node after the tail, inserting at the last position, is faster if you don't need to go through the whole list to get to the tail. So these are the two structures that we'll use. This one for each node, and this one for the whole list. We have a head and a tail, 2 pointers. Okay, now let's discuss a few operations with lists. We'll start with the print, then we'll see how to insert a number at the end of the list, and finally we are going to create a new list. Okay, so in the printing operation, we just want to display in the console all the elements of the list. So if you have the list 10, 7, 12, we would like to be displayed like this. Now, printing the first element is actually quite simple. You just print the key of the head. And this will display 10. Here we have the head. We can take the head from the list structure. And using the head, only the head, we can print the whole list. Because from the head we can get to all the other elements. So if we print the head key, we see the first one. But if you want to print the whole list, we will need a loop. So for example, we can use a while loop and a variable that starts from head and is printed at each step. So at each step we print this variable p, which initially is exactly the same as the head. We start from the head, print its key, and we'll find out the condition later. And in order to move forward, we do p equals p arrow next. So basically, we take, here we had p150. We check what is p next. So it's this element, 700. And we modify p to be p next. And then it will display again, so it will print this 7. Then we move on to the next one, p becomes 300, and we print 12. And when we do p equals p next, this time p is 300, so p next is null. So p next is null. And if we reach the null, we can stop. So in that case, we can use p different from null as the while condition. If you have any questions, don't forget to put a comment or email me or let me know. Okay. So we start from head. While we didn't get to the null, print the key and move on to the next element. And we do it until we reach null. And although this is only the printing function, this is quite a common pattern when working with lists. When you want to do something that requires the traversal of the whole list, you can use this and instead of printf, do whatever you want. So if you wanted to increment each key, so become 11, 8, and 13, instead of this printf, you would put p key plus plus. Basically, whenever you need to go through each element, you use something like this. All right. Now let's move on to the next operation, which is insertLast. Basically, if you want to insert last in this list the key 2, we would like the list to become like this. We have head 10, then 7, then 12. As before, just add this key at the end. And also, you can see that the tail changes. So if we want to write this function, we would need to put a pointer here because our list will change at the end. So whenever some variable changes and it is a function parameter, we need to put a pointer. Alright, so we have a list and we want to add a new key. The first step is to create a new node. To create a new node, to allocate it, you can use malloc function with size of node to create a new node, or you can use the C++ version, which is just node star new node equals new node and parentheses. This is more common in other programming languages as well. Malloc is only in C. Alright, so with this you can create a new node and obtain its address. So you ask C++ or C to create a new node, and it gives you the address at which it had space to allocate it. In this example, it's 800. Okay, we have a new node. Now let's populate it. We can set its key to the given key as parameter. So new node key equals key. Here we put these two. And we can make its next one null. Because we know it's the last element, we can be sure that its next is null. Alright. Now the next step is how can we link this tail to the new node? How can we replace this null with an arrow? So first we want to take the tail, and change its next pointer to our new node. So we would do list tail next equals new node. So we also see here the change. Here we can see here the change that for the last one, the next has changed to 800. Alright, and the final step is to move the tail to the new node. So you can just do this tail equals new node. We move the tail here. Be very careful at these two operations. If you put them in the reverse order, if you first change the tail and then link to the new node, it won't work because it would link the new node to itself. So make sure the order is correct in your code. Okay. And this is the basic algorithm to insert at the end of the list. But there is a special case. What happens if the list is empty? Because initially you don't have any elements. Head and tail are both null. That's how we mark the list as empty. So let's try the previous code and see how it works. So first of all, we allocate a new node. All good. We set the key and the next. All good. But we had a line that put the previous tails next to be the new node. But here the tail is null, so it doesn't have any next, so it will give an error because null doesn't have a next. So in this case, it's better if you add an if. So only if the list is not empty, link the last element to the new node. So we need to add an if here. And afterwards, what we did before, list tail equals new node, will work as well. So we can change the tail to the new node and it's all good. But what should happen with the head? Because the head is still null. Well, if the list was initially empty and we add a new node, the new node should be both the head and the tail. So in this if, we can add an else. So if the list was empty, we also make the head equal to new node. And that way we have both head and tail point to our new node. So basically we replace with this line with this if else to also approach this case when the list is empty. And now this is final. This should work in any scenario. All right. And the final part is how to create an empty list. So in the main function, you can just allocate a new list which contains the head and tail pointers, either with malloc or with new. You can also not use pointers and then pass addresses to the functions, but either way it's fine. I think this way is easier because you don't need to put any ampersands later on. So after you create a new list with head and tail, make sure they are initialized with null so that our functions know that it's empty. Because otherwise there will be some random values and the program will have issues. Alright, so when you want to create an empty list, just make sure the head and tail are initially null. And now this is the coding exercise. So I would ask you, using the discuss code we did above, I also put all of the code in the next slide. Create and print this list. So we have this example. We want to obtain this list, and when we print it, we expect it to show 10, 7, 12, 2. All right. And here are the functions we discussed. So first we have the data structures for node and for the whole list. We have the function that prints. Be careful that this doesn't take the whole list, but only its head. So when you call it, you can use list head. So we have the print function, the insertLast function, and the main function. And here you can put the code. So basically you need to call insertLast 4 times and then call the print function, and that's all. Okay, pause the video here and write down the code. And if you have any questions, don't forget, send them to me. If you want to see more operations with linked lists, you can go on Moodle to the course at Laboratory Resources, and you can find here DSA Lab 2. This one is about linked lists. But if you know these two operations, it's fine by me. So how to insert at the end and how to print. That's enough for me. Alright. Now we're going to talk about two more data structures. These are based somehow on lists, or we can implement them with lists. And the first one is stack. And the whole idea of the stack is that it supports two operations. One of them is push, which means adding one element to the top, and pop, which removes the last element from the top. And it's important to notice that here the elements are added and removed from the same side. And another name for stacks is LIFO, last in first out, which means that the last plated that is added is the first one that's taken. And an example of a stack, we start from an empty stack. If we add the element 7, it will be put here on top. Since we don't have anything below it, we put it on the bottom. Then if we insert 3, we put it on top. But what happens if we push 4? Of course, it will be added to the top. So this is the push operation, which adds one element to the top. Now the pop operation takes the top element out and returns it. So this pop would return 4. And if we do a pop again, which element will it remove? Well, of course it will remove the element 3, because that's the element to the top. And the stack is like something abstract. It doesn't tell you how to do it. It's just what operation should it support. And you can implement stacks using either linked lists or arrays. We will only talk about linked lists in short. So with linked lists, you have two options. Either you use push as insert first. So you use insert first for push and delete first for pop. So each time, first we added 7, then we added 3, then we added 4. And if we were to do a pop, we would remove the 4. Another option is to use push as insert last and pop as delete last. So in that case, we insert 7, then 3, then 4. And if we want to pop, we delete the last one. Now, the issue with the second approach is that delete last is a slow operation. And that is because if you have a lot of elements, many elements, in order to delete the last one, you need to find the previous element. And finding the previous to last element takes a lot of time if the list is very long. Because you need to start from the head and keep going until the next one is the tail. So the preferred version is the one where you insert at the first position and remove from the first position. The other abstract data structure we have is called queue, and queues are similar to stacks. So queues also have two operations, enqueue and dequeue, where enqueue adds an element to one side and dequeue removes the first element from the other side. So here is the main difference between stacks and queues. In queues, you add on one side and remove from the other side. And it's similar to how queues in shops work, because when you come as a customer, you stay ideally at the end of the queue, but the clerk basically serves the people from the first one that arrived. So this is called first in, first out, because the customer that arrived first is served first. Who arrived first is the first one. And they are drawn like this, similar to arrays. So if we in Q7 we add 7 to one side, if we in Q3 we add it from the same side, and if we in Q4 we add it to the right as well. But when we starting DQs, we remove the first element, and the second DQ we remove these 3 and we remain with 4. So it's important that we insert on one side and remove from the other side. And again, even queues can be implemented with linked lists or arrays. We only talk about linked lists. And again, we have two options. Either we enqueue at the tail and dequeue from the head, or enqueue at the head and dequeue at the tail. And again, dequeuing from the tail would be a slow operation, because deleting the last element is slow. So instead, we prefer the first option. So I hope you get the basic theory about queues and stacks, and how you could write the code to do them. And thanks for watching, and don't forget to upload on Moodle the exercise, the one with linked list operations. So you should put there you can put an archive on Moodle. I think only archives are allowed. So you should put your code blocks project or whatever you have. Ideally, you can do the clean before. You should have a build and then clean button, so that you don't put the executable as well. But anyways, just create an zip archive with your code blocks or whatever project and upload it on Moodle. Okay, thanks and good luck. Bye bye.